Okay, so welcome to this next video in the playlist on group theory. In this video what we're going to discuss is the Sylow Theorems. Okay, right. So the Sylow Theorems are theorems about finite groups. They're theorems from finite group theory, and overall there are three separate Sylow theorems, and we're going to state and prove all three of the Sylow theorems in this video. Okay, now, before we go any further, I want to give a warning, okay, and the warning is this. A lot of what we have done up till now in the playlist on group theory has been very, very basic, and the proofs have been very, very trivial. Okay, so we haven't really had any result that's required an extremely hefty proof or an extremely involved proof. This video is where that's going to change. The proofs of the Sylow theorems are not trivial at all, okay, and they involve a lot, basically, a lot of work, and they are difficult to understand. Okay, so my warning is that this is going to be difficult, and if you find it difficult to understand these proofs, do not beat yourself up over it. They are in a different league to what we have done so far in this playlist on group theory. Okay, the other thing that I want to say before we actually begin discussing the Sylow theorems is that there are loads of different proofs of these three Sylow theorems. Okay, I know three different proofs of the first Sylow theorem, and the one that I'm going to give you is in my opinion, the easiest one. Okay, the easiest to understand. In addition, a lot of the other proofs require knowledge about groups beyond what we have done so far. Okay, so I've picked this one because we can do it with our current level of understanding of group theory from the previous videos in this playlist. Okay, so the proofs that I'm going to use for all three Sylow theorems are going to make heavy use of group actions. So we're going to see group actions all over the place. We're going to use group actions all over the place. Okay, right. So with that then, let's actually begin. Okay, and I'll just outline the way that I'm going to do this. So usually when people are discussing the Sylow theorems, the common thing to do is list off all three Sylow theorems and then go through the proofs, starting with number 1, then doing the proof for number 2, and then finally doing the proof for number 3. I'm not going to do that. Instead, what I'm going to do is I'm firstly going to explain the first Sylow theorem, then I'm going to prove it, then I'll give you the second Sylow theorem, then I'll prove it, then the third Sylow theorem, and then prove it. Okay, because I think that when you just chuck all three of them out onto the page, it looks very, very scary when you see it for the first time, and I'd rather that we broke it up basically into little bits so that I don't lose my audience without even beginning a single proof, okay, just by throwing on all three Sylow theorems. The second Sylow theorem in particular looks incredibly complicated when you first see it, okay, whereas the first Sylow theorem, when you just see that one in isolation, that one looks extremely simple. Okay, so that's the way I'm going to do it. I'm going to state the first Sylow theorem, prove it, state the second Sylow theorem, prove it, state the third Sylow theorem, and prove it. Okay, so let's start off with the first Sylow theorem then. So number 1. Okay, so firstly I want to explain what the first Sylow theorem actually says, and as a theorem, the first Sylow theorem is probably the most important, okay, and it's also the easiest to understand. The second one is the most difficult to actually understand what it's even saying, okay, but the first one's very easy to understand what it's saying, but the proof's going to be the most involved. Okay, so let's firstly then discuss what the first Sylow theorem actually says. So firstly, let's start off with the setup. So we need some arbitrary group, capital G, here. So we're going to start off with some group, capital G here. And specifically, this group needs to be a finite group, okay? So we're not interested at all in infinite groups anymore. We're working with finite groups. This is a theorem in finite group theory. Okay, so the order of the group then, the number of elements in the group, the number of symbols in the group, is some finite natural number which I'll call little n. So little n here is some natural number, some counting number, a number that you can use to count the number of symbols. And this is just the number of symbols that are actually within the group. Okay, right. So the first Sylow theorem then is about certain sized subgroups that you can always say are going to exist within the group capital G, okay? And to go any further, what I need to tell you about is the fact that you can factorize the order of the group here, little n, into its prime factorization. Okay, so I'll just remind you what is meant by factorizing a natural number into its prime factorization. So what we will do is we'll rewrite little n here as p1 to the power of alpha 1, p2 to the power of alpha 2, and then we'll go on and on. Okay, so all of these are multiplied together, and we'll go all the way up to pr to the power of alpha r. Okay, so whatever little n is, whatever natural number it is, I can always factorize it into its prime factorization, which will look something like this. Okay, let me make this absolutely explicit. P1, P2, all the way up to PR. These are all prime numbers. Okay, so numbers that are only divisible by 1 and themselves. So these are primes. Okay, and then they're raised to powers, basically. Okay. So alpha 1, alpha 2, all the way up to alpha r, these are their respective powers that they're raised to. Okay, so these are all numbers, okay, between 1 and something else. So they're all natural numbers that are greater than or equal to 1. Okay, so whatever natural number you have, you can always factorize it into a unique prime factorization. We're not going to prove that that's the fundamental theorem of arithmetic, okay, but hopefully your knowledge from classical mathematics will suffice to cover this. Okay, so just to refresh your memory, I'll just give you an example to make this absolutely plain clear. So if the group has order 54, let's say, let's factorize this order into its prime factorization. Okay, so the way that I will proceed is I'll say, oh, that's an even number, so I can instantly pull a 2 out of there, and remember 2 is the only even prime number. Okay, and what will be left over? Well, we'll have 25 from the 50, and then 2 from the 4, so it will be 27. So I can write this as 2 times 27. I'm not complete yet, because 27 isn't a prime number. In fact, that is 3 times 3 times 3, so I can write this as 2 times 3 cubed. Okay, because 27 is 3 to the power of 3. Okay, and that will be the prime factorization then of 54. So you've only got 2 primes appearing in the prime factorization of this number 54. Okay, so in this case, P1 would equal 2, and alpha 1, the power which I'm raising 2 to, would be 1, and P2 would equal 3, and the power alpha 2 that I'm raising 3 to would again be 3. So in this case, little r would be 2. I'd only go up to 2 primes. There's only 2 primes appearing in my prime factorization of 54. Okay, so for an arbitrary group with order little n, I can always factorize its order into the prime factorization in this way. Okay, so now I'm ready to state the first Sylow theorem. So the first Sylow theorem says that there will always exist, okay, so I'll state it here, so here we go. There always exists a subgroup, capital H, which is a subgroup of capital G, such that the order of capital H is equal to pi to the power of alpha I for any I that you like between 1 and r. Okay, so what I am saying basically is you choose any one of these primes in the prime factorization. Okay, so let's say we pick P1 here. I will always be able to find a subgroup in the group capital G of order P1 to the power of alpha 1. Okay, and it's not just true for that prime, it's true for all of them. Okay, and I think I'll colour in the statement of the first Sylow theorem here in orange, since I highlighted first up there in orange. Okay, so not just for P1, you can do this for P2 as well. So we can use P2, we can say P2 raised to the power of alpha 2, I will always be able to find some subgroup in the group capital G which has order P2 to the power of alpha 2. And so on, all the way up to PR to the power of alpha r, there will always exist a subgroup in the group capital G of order PR to the power of alpha r. Okay, so going back to our explicit concrete example here, where we have a group of order 54, what this means is that there will always be a subgroup in this group, at least one subgroup in this group of order 2 to the power of 1 here. That's effectively my p1 to the power of alpha 1, and there will always exist at least one subgroup of order 3 to the power of 3, okay, p2 to the power of alpha 2 here, okay, so 27. Okay, so you can always say that there must exist a subgroup of those orders, and that's what the first Sylow theorem says. So it says that you can always find subgroups of order a prime to its highest power in the order of n. So some prime which appears as part of the prime factorization of the order of the group to its highest power, basically. You'll always be able to find a subgroup of that size. Okay, right. So, what I now want to do then is prove this, but just before I prove this, I'm going to simplify my notation down from this quite complicated notation here to something simpler, okay? Because to prove this, I do not need to be thinking about all the different primes that appear in the prime factorization of the order of the group. Instead, let's just think about one prime which appears in the prime factorization of the order of the group. Prove the first Sylow theorem for that, and then because the prime was arbitrary, we'll have proved it for all of them. Okay, so what I'm going to do is change my notation now, and I'm going to say that the order of the group, we'll still call this little n, but now let's say that this is equal to some prime to the power of alpha times some little n. Okay, so what I'm saying now is I'm only going to be interested in one prime now. Okay, and the prime I'm going to be interested in is this prime p. So this is just some prime that appears in the prime factorization of the order of the group capital G. And I'm saying basically, here is the highest power of p that appears in the prime factorization of the order of the group, little n. Okay, so p to the power of alpha is the highest power of p that I can pull out of little n, basically. And what's left, this little n, is the rest of the prime factorization. So this is the p2 alpha 2 p all the way up to pr alpha r to the power of alpha r. Okay, so the important thing that I know about little m here is that there is no power of p left in it. So p does not divide little m. Little m is not a multiple of p. So that's an important statement that I've got there about this number, little m. But other than that, it will be some natural number that's left over once you've pulled out the highest power of p that you can from little m. Okay, right, so what I now want to prove then is that I can find a subgroup of capital G of order p to the power of alpha always. Okay, and since this is an arbitrary prime and this is an arbitrary group, I will then have proven the first Sylow theorem. Okay, right, so just before we begin the proof, I just want to give you a little bit more nomenclature, okay? And the nomenclature that I want to give you is the nomenclature of what is meant by a p subgroup, okay, and what is meant by a Sylow p subgroup. But let's start off with what is meant by a p subgroup of a group capital G, okay? So a p subgroup of capital G would be a subgroup, okay, so I'll show this. So it's a subgroup capital H, which is a subgroup of capital G, such that the order of capital H, okay, such that the order of capital H is some power of p, okay, so it's some p to the power of beta, okay, where beta is some natural number that is less than or equal to alpha, but greater than, or equal to 1, no, that's fine, okay, so it's some subgroup that the order of which is some power of this prime p. So that is what is meant by a p subgroup of G. Now, if it's a very special p subgroup, if the order of H is actually equal to p to the power of alpha, the highest power of p that you could possibly have a subgroup having its order equal to, and let me just explain why you can't have a power of p higher than this. Okay, remember Lagrange's theorem tells us that the order of the group must divide the order of the subgroup must divide the order of the group. The order of the group must be a multiple of the order of the subgroup. If we had a higher power of p here for the order of the subgroup, then it would no longer be the case that that divides the order of the group, and therefore it couldn't possibly be a subgroup. Okay, so for any subgroup of the group capital G, you cannot have it having order a power of p that's higher than alpha. Okay, but you could have it going up to alpha. Okay, and these are these special subgroups that the first Sylow theorem tells us about the existence of. Okay, so subgroups of order p to the power of alpha, where alpha is the highest power that p appears in the prime factorization of the order of the group, are now called Sylow. Oops, and I've missed off the y. Sylow p subgroups. Excuse that strange y that I've drawn there. Okay, I was about to put the L there. Okay, so these are called Sylow p subgroups. So the first Sylow theorem tells us that Sylow p subgroups will exist for any p that appears in the prime factorization of the order of the group capital G. Okay, and that's what we're going to go and try and prove now. One final bit of nomenclature, however, before we do that. Okay, the final bit of nomenclature is that the set of all Sylow p subgroups of G is denoted like so. Okay, so SYL for Sylow, subscript p, and then brackets G. Okay, so this is the set containing all Sylow p subgroups. So you find all of the Sylow p subgroups in the group capital G, stick them all into this set, and that is what is meant by this notation here. So H is an element of the Sylow p subgroups if it's a subgroup of capital G of order p to the power of alpha, if it's a Sylow p subgroup, basically. Okay, right, and that's the final bit of nomenclature that I want to do. Okay, so we're going to now try and prove the first Sylow theorem. So we've got our arbitrary group here, which has order n, it's some finite group. We've factorized this into p to the power of alpha times n, and we've pulled the maximum power of this prime p we possibly can out of little n rather, so that little m here is not a multiple of p. P does not divide little m. And we want to now prove that there is some subgroup of our group capital G which has order p to the alpha. We want to prove that there is a Sylow p subgroup. Okay, so how are we going to do this? Well, to find a proof of this, someone has sat for a very, very long time and thought long and hard and come up with some ingenious, convoluted way to actually get there. Okay, and it's something that you would not come up with in 10 minutes. It's something that has taken someone a lot of experimenting to try and actually come up with. Okay, and for that reason it's quite difficult to motivate this proof, but I will try my best. Okay, so what we're going to consider is a set called curly C. Okay, I'm going to call it curly C. Okay, and this set is going to be a set of subsets of the group capital G. Whenever you see a curly symbol like this, it usually means a set containing subsets. Okay, so curly C, I'm going to define curly C to be the set, okay, containing all subsets of my group capital G. Okay, and I'll call an actual subset non-curly C, so just capital C. So it's all capital C, which is a subset of capital G, such that the order of capital C, the number of elements in capital C, is equal to this special number p to the power of alpha. Okay, now that is quite a natural thing to be looking at if you're trying to prove the first Sylow theorem, because somewhere within this will be our Sylow p subgroup if it exists. Okay, so we are going through every possible subset of our group of order p to the alpha. Okay, so if I draw a picture for this, here is my group capital G here. This is the set of symbols of the group anyway, so I'll colour this in red here. So here is my group, and what I'm now going to do is I'm going to look at every possible subset that you can possibly construct of the set that underlies the group that has order p to the power of alpha. Okay, so here is my subset C, and I'll colour this in orange here. Okay, and the key property that C has is that it must have order p to the power of alpha, and you take every possible subset that you can possibly construct, stick every single one of them into this great big set, and that's the set that I am now calling curly C here. So it's a set of subsets of the group capital G. Okay, and it's a natural enough thing to consider because one of these subsets will be my C of P subgroup if it exists, basically. Okay, so most of these subsets are not even going to be subgroups, okay, but somewhere within that must be my C of P subgroup if it actually exists. So that's the reason why this is a natural enough thing to actually consider. Okay, the next thing that I want to show you, okay, which we're going to make incredible use of later, but at the moment is difficult to motivate why you would care. Okay, so just go along with it for now and you will see the big picture of where this is all going to fit in later. Okay, is that the prime P does not divide the order of curly C. Okay, so what I want to prove is that the size of this set curly C, okay, the number of all the total number of all subsets that you can take of the group capital G which have order p to the power of alpha, the total number of those, it's not a multiple of p. P does not divide it. Okay, that's the first thing that I want to prove, and we're going to use this to prove the first Sylow theorem later. Okay, but for now, don't try and understand why this is important, just try and understand the proof that this is the case. Okay, so how are we going to prove that this order of curly C is not actually a multiple of P? Well, firstly, let's try and get an explicit formula for the order of curly C, and amazingly, we can actually do that using combinatorics. Okay, so I would like a formula for the order of curly C. Okay, so the order of curly C is going to be exactly equal to the number of possible subsets of order p to the power of alpha that you can take in this group capital G. And remember, the size of the group capital G is equal to little n, which we know is equal to p to the power of alpha times m, and that's important. Okay, so how many possible ways are there of choosing p to the alpha elements from n elements? Okay, well, hopefully you've studied combinatorics at some point in your life and you know that this is n choose p to the power of alpha, but I'll just repeat in brief the argument as to why this is true in a moment. Okay, so let's just firstly write out what the explicit formula then for n choose p to the power of alpha actually is. Okay, well, remember that this is equal to n factorial over n minus p to the power of alpha factorial times p to the power of alpha factorial here. Okay, that's just the definition of what it means to take n choose p to the power of alpha. Okay, now let's just write that out in a more explicit form. Okay, so let's expand the factorials and cancel this one with this one. Okay, so when we write this out properly, what we'll get on the top is n times n minus 1 times n minus 2 times all the way down to, what will we get up to? Well, we won't quite get up to n minus p to the power of alpha, because n minus p to the power of alpha and all the bits below that will be cancelled by this portion below. So what we will get down to is n minus p to the power of alpha plus 1, the term prior to n minus p to the power of alpha. Okay, and I'll just try and straighten this a little bit, there we go, and move it up, I think, as well. Okay, so that's what we're going to have on our numerator. Okay, and I might use this line to actually denote the fraction portion here. Okay, so now we've sorted out the n factorial and the n minus p to the power of alpha factorial. So this portion has cancelled the rest of the n factorial. And now all I need to do is put the p to the power of alpha factorial in the denominator. Okay, so what we'll have is p to the power of alpha times p to the power of alpha minus 1 times p to the power of alpha minus 2, all the way down to what we'll have at the bottom here will be 1. However, there's a way that's nicer to write this, and hopefully you'll see why in a moment. Okay, so instead I'm going to write this as p to the power of alpha minus something, and what will we have to minus off? Well, we'll have to minus off p to the power of alpha plus 1. Okay, and hopefully you can see why it might be nice to write 1 in this strange form as p to the power of alpha minus p to the power of alpha plus 1. It's because it looks very similar to what we have at the top here. Okay, and indeed that's going to be useful later on. Okay, right, so this is our explicit formula then for the order of the set curly C. Okay, so let me now just give you the argument as to why this is actually the number of possible subsets that you can construct of the group capital G of order p to the power of alpha. Okay, and the reason is that if we want to construct a subset of order p to the power of alpha, then we firstly have to choose the first thing that we want to go in here. How many different things are there to choose for the first thing that can go in here? Well, there is little n things that you can choose for the first thing to go into our subset capital C here. And then for the second thing that you want to put in, how many things are there to choose from? There's n minus 1 possibilities, because you've already used up the first thing from the group that you put in to the subset C. Okay, and so on, and you'll go all the way down to choosing your p to the power of alpha thing, and what will be left over then will be n minus p to the power of alpha plus 1 things, okay, because you've already put in p to the power of alpha minus 1 things. So you're subtracting off p to the power of alpha minus 1 here, and the minus is on the 1 has cancelled with the minus to give you a plus here. Okay, so that's the number of ways of choosing the final thing that you're going to put into this subset. Okay, and now there's a problem with that, and the problem with that is that overcounts. Okay, that counts the same subset loads of different times, and the reason it counts the same subset loads of different times is it counts all the different ways that there are of constructing the same subset but putting the elements of the subset in different orders. That's the problem with this. This takes into account all of the different orders that you can put the elements of the same subset in to create the same subset. Okay, so that's why if we just had this expression in the numerator, it would completely overcount, because it would take into account all the different orders that you can actually put the elements of a subset into that subset to construct it. Okay, so what we now need to do is divide through by the total number of ways that there are of ordering the p to the power of alpha elements in a subset of size p to the power of alpha, and that is p to the power of alpha factorial. Okay, so that's why we're dividing by p to the power of alpha factorial, to take account of the fact that we have completely overcounted here. Okay, we've counted all of the different orders that you can put in the elements as separate subsets, when of course loads of them are going to be the same subset, just we've put in the elements of that subset in different orders, but it's the same subset fundamentally, and we don't want to count those as separate subsets. Okay, so that's why we have to divide by p to the power of alpha factorial. Okay, so this is the explicit formula then that we've got for the order of this set curly C. Okay, and what we now want to prove then is that the prime p does not divide this number. Basically, we want to prove that it does not divide curly C. Okay, so what we need to prove is that p doesn't divide this number. Now before we do that, what I want to do, and in fact to prove that it's going to be helpful, to rewrite this in a more helpful format, a simpler format. Okay, and the way that I'm going to rewrite this is as the product. Okay, so this big pi symbol means the product from k is equal to 0 to p to the power of alpha minus 1 of n minus k in the numerator over p to the power of alpha minus k in the denominator. Okay, so this is just exactly this. This is just a simpler way of writing it. Okay, so what this means is go through k is equal to 0 all the way up to p to the power of alpha minus 1, and take all of these terms for those different values of k and multiply them all together. Okay, so it's similar to a series, but we are multiplying the terms rather than adding the terms. Okay, right, so let's just explore why this is going to be equal to this. Well, when k is equal to 0, we'll get n in the numerator and we'll get p to the power of alpha in the denominator. That gives us this portion here. When k is equal to 1, we'll get n minus 1 in the numerator, and we'll get p to the power of alpha minus 1 in the denominator. That will give us this portion here. We'll multiply those two first terms together to get this portion, and we'll go on and on all the way up until k is equal to p to the power of alpha minus 1, and we'll get n minus p to the power of alpha. The double negative will cancel to give us plus 1 here, and then in the denominator we'll get p to the power of alpha minus p to the power of alpha plus 1 as well. Okay, so indeed this thing is equal to this, and it's a nice, more concise way of writing this. Okay, so now what we want to prove then is that our prime, little p here, does not divide this great big number that we're constructing here. Okay, now to do this, it's going to be helpful to firstly substitute in for little n here, p to the power of alpha times n. Okay, so I'm just going to substitute in the fact that little n can be factorized into p to the power of alpha times n. Okay, where m is not a multiple of p, there's no powers of p left in little n. Okay, the other thing that's going to be very helpful to do here is take our little k and factorize that into its prime factorization. Now I know little k is a variable. Little k is going to vary from 0 to p to the power of alpha minus 1, but for any one of those terms in the product here, k will be a constant, and for each one of those you can factorize little k. Okay, now I'm going to factorize little k into something of the form p to the power of I times L. So I'm going to put out the highest power of p that it contains. Now you might be saying, well hang on, what if it doesn't contain a power of p at all? What if it's not a multiple of the prime p? Well, I'm going to say now that little I can actually be equal to 0. Okay, so for many k's that aren't multiples of this prime p, indeed I will be 0. Okay, but we're still going to pull out the highest power of p that this k actually contains. Okay, and there's another thing that we can say about I. We can say that it's going to be greater than or equal to 0, but we can also say that it's going to be strictly less than alpha, and that's going to be so important. Okay, that's strictly less than alpha. Okay, and the reason we can say that it's strictly less than alpha is that k only ever gets up to p to the power of alpha minus 1. Okay, so it's never going to be able to get a power of p here that is greater than alpha or even equal to alpha, because it never gets up to p to the power of alpha. Okay, so we don't need to worry about I even getting up to alpha. It's going to always be strictly less than alpha. So for any k, I can rewrite it as some power of p, and often that power of p will be p to the power of 0, okay, times some L which doesn't have a single power of p in it. That's the important bit, that L is going to be some number that is not a multiple of p, so p does not divide L. Okay, so for any k from 0 to p to the power of alpha minus 1, I can do this to it. I can pull out the highest power of p that it contains to leave something, this L, which is the remainder, which has no powers of p in it. Okay, so what I'm now going to do then is substitute these things in here basically. Okay, and I will change this into the product from k is equal to 0 to p to the power of alpha minus 1 of p to the power of alpha times m, so I'm just substituting in n here, minus p to the power of I times L over, and now we've got p to the power of alpha in the denominator here, minus, and then again I'll replace k with p to the power of I times L. Now note, I and L are not constants. I and L will be functions of k, so they will vary as k varies. Okay, but these two important facts that I've got about them, that I is always less than alpha and p does not divide L, those facts will not vary, and those facts are all that I need basically. Okay, so here is my expression here. Okay, and what I'm now going to do is pull out powers of p from the numerator and the denominator here. And I think I'll just transfer onto the other side of this piece of paper. So let me firstly just, let me get it nice and straight first. Okay, and let's transfer the equation that I now have for the order of curly c. So the order of curly c is this product from k is equal to 0 to p to the power of alpha minus 1 of p to the power of alpha times m minus p to the power of I times L, that's my k, okay, over p to the power of alpha minus p to the I over L, okay, and what I know, remember what I know, is that p does not divide L, okay, and that I is between 0 and it's less than alpha, okay, so it's greater than or equal to 0 and it's less than alpha. Okay, so these two facts are going to become extremely important. Okay, so what I now want to do then is the obvious thing. Let's factorize out some powers of p. Okay, so what I'm now going to do is I'm going to rewrite this like so. Okay, so again it's going to be the product from k is equal to 0 to p to the power of alpha minus 1. Okay, and I'm going to pull out this p to the power of I. Now remember, I is less than alpha, so p to the power of alpha here is a greater power of p than this. Okay, so what I'll then get is p to the power of alpha minus I, and this will still be a positive natural number basically. Okay, so that's all good. And then we'll get m here, and then it will be minus L. And then in the denominator we can do the exact same thing. We can pull out p to the power of I, and we'll get p to the power of alpha minus I here, minus L. Okay, right, and that's now our formula for the order of this set curly C. And what we can obviously do here is for each of these terms we can cancel this p to the power of I. And again I want to stress that yes, I varied for k, but this is a single term here, so at the moment I is constant. For a single term I is going to be constant, and in every single term therefore you can cancel this p to the power of I. Okay, so indeed we'll do that, and this will then be equal to the product from k is equal to 0 to p to the power of alpha minus 1 of, in the numerator we'll have p to the power of alpha minus I times m minus L, and in the denominator we'll then have p to the power of alpha minus I minus L. Okay, right, and what we want to prove, remember, and you might have forgotten by now what we were actually trying to prove here, we want to prove that this great big expression, which is still the order of this set curly C, the number of subsets of the group capital G of order p to the power of alpha, we want to prove that this great big expression is not a multiple of p. We want to prove that p does not divide this. Okay, so how are we going to do that? Well, let me just remind you of the fact that although this expression looks horrendously complicated, and although it looks as though it could give out some horrendous number, some horrendous fraction, it will not, in fact, because remember it is a formula for the order of this set, curly C, and this order of this set, curly C, is some beautiful natural number. So even though this looks horrendously complicated, the actual answer it will spit out in the end is going to be extremely simple. Okay, and what I would like to do, one final last modification I'd like to make to this is to split it into one huge numerator divided by one huge denominator, and this will actually help us. Okay, so I want to now acknowledge the fact that if we are multiplying all these terms together, then what we could actually do is split it into the multiplication of all of the numerators together and then just divide that by the multiple of all of the denominators together. So I'm now going to split this into two. So the product from k is equal to 0 to p to the power of alpha minus 1 of all of the numerators, p to the power of alpha minus I over m minus L, and then I'll have the denominator here, and the denominator will be the product from k is equal to 0 to p to the power of alpha minus 1 of p to the power of alpha minus I minus L. Okay, so I've just split it up like so now, and that's a perfectly valid thing to do, because remember this just means multiply all of the terms together, and now what I'm saying is we can multiply all of the numerators first and then just put it over the multiple of all of the denominators, and that's exactly the same thing. Okay, right. So, remember the fact that this will chuck us out some beautiful natural number, and what that means is that if we were to look at the prime factorization of the numerator and the prime factorization of the denominator, all of the powers of the primes that appear in the prime factorization of the denominator would have to appear in the prime factorization of the numerator, because the overall answer has to be some beautiful natural number. Okay, it can't be a fraction, basically. It has to be some beautiful natural number. So it has to be the case that all the powers of the primes in the prime factorization of the denominator have to just cancel with powers of primes that we have in the prime factorization of the numerator. Okay, now that means that if I want to prove that p does not divide the order of curly c, p does not divide the entire thing here, basically. I want to prove that there's no power of p in the overall answer, in the prime factorization for the overall answer, then it would suffice to show that p does not divide the numerator. Okay, because if there's no power of p in the prime factorization of the numerator here, then how could there possibly be a power of p in the entire thing, in the prime factorization of the entire thing? Because as I've just explained, all of the primes that we have in the prime factorization of the denominator are just cancelling with primes that we have in the prime factorization of the numerator. Okay, so if I can prove that there's no power of p appearing in the prime factorization of the numerator, then I'm done, because all this is doing is getting rid of a whole bunch of primes that appear in the prime factorization of the numerator, nothing else. So if it's not in there in the numerator before it's had this cancelling out loads of powers of primes, then it's certainly not going to be in there afterwards. Okay, so what it will suffice to do is prove that p does not divide the product from k is equal to 0 to p to the power of alpha minus 1 of p to the power of alpha minus I times m minus l. Okay, so this is our final challenge, to prove that p does not divide the numerator here, this thing here. Well, if I want to prove that there's no power of p appearing in the prime factorization of the entire thing, then it would be good enough to prove that p does not divide any of the terms here, because if p isn't a multiple of any of the things that we're multiplying together to get the entire thing, then it's going to be the case that when we do multiply them all together, it's not going to appear in the prime factorization of the entire thing. So if it were to appear in the prime factorization of the entire thing, it would have to appear in the prime factorization of one of the terms, because when you multiply two things together, you just effectively combine their prime factorizations, you add the powers of the primes that are involved. Okay, so what I now want to prove is that for all k, okay, so for all k is between 0 and p to the power of alpha minus 1, p does not divide this term, okay, which is p to the power of alpha minus I times m minus l. Okay, and if I prove that p does not divide any of these terms, then I will have proven that it does not divide the product of all of them. Okay, and therefore I will have proven that p doesn't divide this numerator, therefore it doesn't divide the entire thing, and that entire thing is equal to the order of this set curly c, so p doesn't divide the order of the set curly c. Okay, right, so how am I going to show that p doesn't divide this? Well, I'm going to use these two facts that I know are always true, no matter what k. Okay, I know that p doesn't divide l, so l is not a multiple of p. Okay, the other key fact that I know is that I is always less than, and it's not less than or equal to, it's less than alpha, and it's something greater than or equal to 0. So that tells me that p to the power of alpha minus I is some positive power of p. Okay? Always. No matter what k you have, it's always some positive power of p. So we have some positive power of p times some number m. This is some multiple of p. Okay? Quite clearly, because it's got some power of p here. And I am then taking off, or effectively adding, the negative of a number that is not a multiple of p. What happens when you take a multiple of p and add on something that is not a multiple of p? Well, you end up with something that's not a multiple of p. Okay, so just to draw a picture of this, if this is the number line, let's mark on the multiples of p. So we'll have 0 here, we'll have p here, we'll have negative p here, we'll have 2p here, we'll have negative 2p here, etc. So these are the multiples of p. Okay, Now, if you have one of these and you add on to it something that is a multiple of p, then effectively you'll be jumping between multiples of p because the gaps between multiples of p are multiples of p themselves. Okay, so to take an example, if you have 2p here and you subtract off p, you'll end up back on another multiple of p because you've bridged the gap between one multiple of p and another multiple of p. If, on the other hand, you take a multiple of p and you subtract off something that is not a multiple of p, which we know L is not a multiple of p, you will end up with some answer that is not a multiple of p because you have not jumped over the gaps between two multiples of p. Okay, so because you are adding on something here which is not a multiple of p, then it's going to take this multiple of p to something that is overall not a multiple of p. So you've got a multiple of p, you are adding on the negative of something that is not a multiple of p, and that overall gives you something that is not a multiple of p. Okay, so for whatever k you are dealing with, this argument applies that you have a multiple of p here and you have something that is not a multiple of p here. Okay, so these things, these terms in this product are always not multiples of p. Okay, so that means that the entire product of them is still not going to be a multiple of p, because when you multiply together loads of things that do not have p in their prime factorization, the overall thing will not have p in its prime factorization. So what we have now successfully proven then is that p is not a does not divide the order of the set curly C. Curly C does not have a power of p in its prime factorization. Okay, and we will use this fact to prove the first Sylow theorem. Okay, so I think we'll have a break there, and in the next video what we will do is we will indeed use this fact to prove the first Sylow theorem.